Alrighty, lads and ladies, welcome back. Today we are going to move away from polynomials a little bit and start talking about a different family of functions. A lot of the polynomial stuff is still going to be important though, because the new functions we're talking about are what are called rational functions, and these are built up out of polynomials. So while we are kind of moving away, it's we're kind of just moving next door. From here, we will start talking about inequalities involving rational functions. And throughout all of this, the business of like multiplicities and local behavior is going to be very important. So just be mindful of that. We're kind of starting something new, but we're kind of not. We're also just building on where we were before. There's going to be some new notation, some new concepts, stuff that you've probably seen in a previous algebra class somewhere, but maybe not with a lot of care. If there's one word that people associate with the study of rational functions at this level, it's the word asymptote. So today we're going to talk a lot about asymptotes. Let's go ahead and dive in. Ready? So this is MAC1140, section number 009, which is pre-calc. And the date today is the 14th of October, 2021. Today we're talking about rational functions. Which is section 3.6. Now with my class on Monday, I got a feel for kind of how well received this material is. And the feeling I walked away with was that we need to spend a little extra time here. So we're not going to just blow through 3.6 today and then blow through 3.7 on Tuesday and then have the test next Thursday. Y'all need more time, which is okay. So today we're going to do kind of our first lecture on rational functions. And then on Tuesday of next week, we're going to do another small lecture on rational functions before starting on the inequalities section. So associated with those, they're going to be multiple homeworks from this section. You may have noticed I opened up a new homework set for you guys already, and that is section 3.6 part 1. So there will be a part 1 and part 2 to our rational function homework. And what we're going to learn today is the stuff that you need to complete part 1 of that. So the only place to get started when introducing a new family of functions is with a definition. That's where we got to begin. So what are rational functions? You may recall I said that polynomials are like the function version of whole numbers, right? Polynomials are like the function version of the integers. And in the same way that the rational numbers are what you get by looking at ratios of integers, rational functions are ratios of polynomials, i.e., a rational function is one of the form, I'll use R of X, R for rational, equals P of X over Q of X, where the functions P and Q are polynomials. And so this is the definition of a rational function. It's a function that can be written as some polynomial divided by another polynomial. And we've seen a number of these, right? A bunch of our, let me pull it up, a bunch of our parent functions are rational functions. So first off, every polynomial is actually a rational function, but these are the ones that are kind of more obvious examples of rational functions. I'm going to start today by looking at just one of these. This guy. So maybe a quick note here. Let's write down what we said. Where's my light blue? So every polynomial is technically a rational function. In that same way that every integer is also a rational number, where the denominator q of x is 1. Remember, constant functions are technically polynomials, right? This is just a polynomial of degree 0. So if you have your favorite polynomial p of x, that is already in this form p of x over q of x, where q of x is just the constant polynomial 1. So this can be a source of sneaky questions, right? Is such and such function a rational function? If you're asked that about a polynomial, then the answer is yes. For the same reason that 5 is a rational number, x squared minus 2x plus 7 is a rational function. They can both be written as fractions, just the denominator happens to be 1. Now, more interesting example, the first kind of simple example of a rational function that exhibits the behaviors that we normally associate with rational functions. 1 over x. This is a rational function. Here, the numerator, p of x, is 1, which is a degree 0 polynomial. And the denominator, q of x, is just x, which is a degree 1 polynomial. So this does fit this definition. That's all we're saying there. The graph of 1 over x is one you should know because it is one of our parent functions. Just to remind you quickly. And we like to draw in these lines that you see the function kind of getting closer and closer to as dotted lines called asymptotes. Some points that are on this graph. 1, 1, right? If you plug in 1 for x, you get 1 over 1. 2, 1/2 is a point on this graph, right? Because when you plug in x equals 2, you get out 1/2. Over here, you have a point -1, -1. So there's a few points on the graph of this function. As I said, these dotted lines have names. This dotted line here is called a horizontal asymptote. And if I wanted to describe this particular horizontal asymptote, this horizontal line right here is the line y equals 0. And this vertical dotted line is called, not very clever with the names, is called a vertical asymptote. And this particular vertical asymptote is the vertical line x equals 0. And I'd like to begin here by asking, where do asymptotes come from?
They're basically whatever the function can't take as an input, I believe.
It's true that vertical asymptotes, the x value of that vertical asymptote is going to be an x value that this cannot take as an input. That's true. But why do we have this behavior? Why does this arrow go way up here? Why does this arrow go way down here? Why does the graph have that shape where it like blows up to infinity as we get closer and closer to zero, or blows up to negative infinity as we get closer and closer to zero? Why does it do that? And similarly, why does this function want to get really, really close to zero as we walk far off to the right? Why does this output want to get really, really close to zero as we walk really far to the left? What's the cause of that behavior? The answer, sorry, go ahead. Yeah.
Because the function is undefined, so it can be everything else except for zero.
That's true, and that's similar to the answer that was just provided. I'm sorry, I couldn't see who that was that said that a second ago, but yeah, it's true that the function is undefined at zero. That's certainly true, and it would be also true to say that the domain is everything except for zero, but that still doesn't quite explain why this blows up here, right? Why doesn't it do something else and just have like a hole there? Isn't that possible? And the answer here is coming from arithmetic, believe it or not. If you take the number 1 and you divide it by a very big number, what do you get? And we're speaking here, of course, qualitatively, not quantitatively. But what happens if you divide 1 by a huge number?
You get a very small number.
Yeah, you get something really, really small. So as my x values get really, really big, meaning I'm walking very, very far off to the right here, the y values, which is 1 over that x value, is going to be a very, very small number. By small, we mean close to 0. And on the other hand, if you take 1 and you divide it by a very, very small number, you divide 1 by a number that is itself very close to 0. So that's like what we're doing when we look right here, right? Like this x value would be a very, very small number. And when I divide 1 by that, I'm going to get a very, very big number. Something that's, you know, close to infinity, if you'll let me be kind of sloppy about it. So why the vertical asymptote? Why this shape? Why this arrow blowing up down here or this arrow blowing up here? Well, it's because if you put an x value in here, which is close to 0, something like 0.001, you're going to get out a huge number like 10,000. So this thing goes up, 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 up as the x values get closer and closer and closer to 0. And the same sort of logic explains the horizontal asymptote. Why is this graph getting so close to the line y equals 0 as I wander further and further out here? Well, that's because when you take 1 and you divide it by a very big number, you get something that is very small, very close to 0. And that's exactly what this function does. It takes your input and divides 1 by that number. So if you divide 1 by a big number, if you're talking about plugging in big ass x values, then you're going to get out a number that is very close to 0. So the further you wander from the origin here, the further you go to the right, the closer this graph is going to get to the line y equals 0. And the closer you get to 0, the further you wander in towards 0, the larger the output is going to get. And that's where this sort of behavior is coming from, right? As I get closer to 0 with my inputs, like look here, here's 0.1. The output is 10. If I were to look at 0.01, can I find it? Can I click it? It's not gonna. If I look at 0.01, there it is, then the output is going to be 100. Right, so the closer we get to x equals 0 along this graph, the closer we get to an x value around here, the larger this piece is going to be. Why does this side go up and this side go down? Well, that's because if you plug a very small negative number in, then you're going to get a very large negative number out. If If you plug a very small positive number in, you're going to get a very large positive number out. And the same thing is true over here. If you plug a gigantic negative number in, then 1 divided by a negative, well, it's going to be negative. Positive divided by negative is negative. And the size is going to follow this rule. So the reciprocal of a big ass number is a small ass number. There is a special notation for these. And it's the same notation that we used for end behavior with polynomials, with one small modification. So we're going to use the goes to notation here. As x goes to negative infinity, as I wander very far off to the left, the y values on this graph are going to 0. But we want to encode a little bit more information than that. See, I want to know whether this arrow is like sneaking up on this line from underneath, like it is over here, or from above, like it is over here. So to indicate that this thing is going to 0, but staying negative, I put a little minus right here. A little superscript minus sign. And then to describe the end behavior on the right, to describe the horizontal asymptote over here, I would say as x goes to positive infinity, y is again going to 0, but this time we're sneaking on 0 from above. Those y values are positive, so we write 0 plus like this. And this is a notation that you'll learn to use more in Calc 1 when you talk about one-sided limit functions, the first week or so of Calc 1. That notation which we use for end behavior, that goes to notation for end behavior, also works well for describing vertical asymptotes. So if I wanted to describe this vertical asymptote, x equals 0, and the kind of local behavior near that vertical asymptote, I can again use this goes to notation. I can say as x goes to 0, and I'm going to talk first about this piece. As x goes to 0, y goes to positive infinity. But how do you know I'm talking about this piece and not this piece, right? This would be wrong if I was talking about this piece. And the idea is that when I'm talking about this piece, x is getting closer and closer to 0, but it's positive. So I would say as x goes to 0 plus y goes to positive infinity. And similarly, as x goes to 0 from the left, as x goes to 0 coming in from this side, meaning I'm plugging in numbers that are a little bit less than 0, then my y values are blowing up, but they're blowing up down towards negative infinity. So I'd say as x goes to 0 minus, y goes to negative infinity. So this orange notation is a really nice way to describe the behavior of a function near its asymptotes, whether we're talking about vertical asymptotes or horizontal asymptotes. And you'll see that figuring those out is actually very important for drawing graphs of more complicated rational functions. Okay. Any questions about these things here so far?
I know how you found the vertical asymptote. Would you just put y equals 0 for the horizontal asymptote? Okay, all right, cool. Sorry, I didn't see that. No.
No, that's okay. Yeah, if I wanted to describe this, so remember horizontal lines. Let me clear just move on the graph. I want to describe a horizontal line. Those are always just y equals a constant, right? So the horizontal line y equals 0 was our asymptote here, and the vertical line x equals 0 was our vertical asymptote here. Let me sketch these in with the graph of 1 over x.
How do we go about finding the asymptote if we don't have the graph? Is there just an equation or a formula for that?
There are, yes, I'll
Okay,
show you.
cool.
So I'm going to give you a procedure for finding both vertical and horizontal asymptotes in just a minute. But before
Sure,
we
I was
do
just
that-
making sure you didn't already do that.
Oh, no, you're good, you're good. Not quite yet. But first, since this 1 over x graph is a graph that we know so well, I'd like to talk about transformations of this 1 over x graph, because there are a lot of simple rational functions. For example, if you took college algebra here at Santa Fe, every rational function that you were required to graph in that class can be graphed as a transformation of this guy, right? You just slide him around, up, down, left, right, flip him over, stretch him out, whatever. All of those functions from college algebra that had asymptotes can be looked at as transformations of this guy. So let's do a little bit of that, because it can be very simple, but it can also be slightly non-simple. So transformations of 1 over x. Any rational function of the form linear over linear, so like ax plus b over cx plus d, can be graphed as a transformation of y equals 1 over x. And it's sometimes obvious how to do this, sometimes not. So I'd like to look at 2 examples. The first one I think is fairly easy, and the second one I think requires a little bit of thought. So let's sketch r of x equals 1 over x minus 3, and r of x equals, how about x over x plus 2 as transformations of y equals 1 over x. Looking at that first function, 1 over x minus 3, is kind of similar to the problem from the test. What transformation do I need to apply to 1 over x to get 1 over x minus 3? So my parent function is 1 over x. To get this guy from 1 over x, what do I do?
I know that you either move it to the right or left because it's inside the parentheses. I think it's to the left.
Almost. So remember, the horizontal stuff is kind of the opposite of what you would think. So this is going to be a shift. You're correct, that's a horizontal shift. We're going to shift right by 3 units. And after I give you the rule for finding vertical asymptotes, you'll see another way to think of that. The downstairs here would be 0 when x is equal to 3. So your vertical asymptote is going to move from x equals 0 to the right to x equals 3. But this is just thinking about it as a transformation. There's only one transformation here, and it's a shift right by 3 units. So if I start with y equals 1 over x, quick sketch of him. And I drag everything to the right by 3 units. Let me track a few points. I'll just track -1, 1, -1, -1, and +1, +1. Just track these 2 points for now. That's okay. And I shift everything to the right by 3 units. Draw on these asymptotes. One of my asymptotes will change. The other one will not. Which one does not change?
Horizontal one?
Good. The horizontal asymptote isn't going to be affected by moving left or right. So let's take a look at what I get. If I do move everything to the right by 3 units, here to 1, 2, 3, my vertical asymptote is going to move, right? Because I picked the whole thing up and shift it to the right. but my horizontal asymptote is not. And in general, when sketching these rational functions, I like to start with the asymptotes. Then the point 1, 1, if I move that to the right, 1, 2, 3, is going to become 4, 1. The point -1, -1, if I move that to the right, 1, 2, 3, he's going to become 2, -1. And the shape of the graph is the same. All I've done is pick it up and move it to the right. So here's my new graph. This is r of x equals 1 over x minus 3. Now, this one, not too bad, right? Not too bad to see the transformation. Not too bad to do the transformation. Any questions on where this graph came from? Okay, looking at the second guy, if it was just 1 over x plus 2, that would be a shift to the left by 2 units, but it's not. The numerator isn't a 1, and there is no transformation associated with multiply by x, right? If you multiply by a constant, that's a vertical scaling. But if you multiply by x, that's not any of our transformations. So what the hell can we do here?
Could you just plot points?
You could, but remember, we want to graph these as transformations. So our goal is to do some algebra to this thing so that we can see the transformation. Could plot points, but that's not a very appealing approach. We want to avoid plotting points in general. The trick is to divide. If I divide x by x plus 2, I'll get some number plus some remainder term with an x plus 2 downstairs. So if we do the long division, I'll show you another way to do this too. I'm dividing by x plus 2, and the thing I'm dividing is x. So it would look like this. Lead terms only. So what times x is equal to x? Well, 1 times x is equal to x. And then I distribute 1 times x plus 2 is x plus 2. And then I subtract one row from the other. I guess I should write this as x plus 0 if we're being careful. X minus x is 0. 0 minus 2 is -2. So this means that x over x plus 2 is the same as 1 plus -2 over x plus 2. All right, that's the result from that long division written in the form q plus r over d. So my rational function r of x can be rewritten as, I'll write it as 1 minus 2 times 1 over x plus 2. And then maybe one more little thing rewriting this, I could write that as -2 times 1 over x plus 2 plus 1. And now I think we can see the transformations. So let's start with the x plus 2 here. If I'm just looking at this piece, 1 over x plus 2, what transformation do I need to apply to 1 over x to get this guy?
Horizontal shift to the left.
Good. Yep, left by 2. All right. What about this? Let's focus on the negative first. So multiplying this whole thing by a negative does what?
I think it flips it across the y-axis.
Well, almost flips it vertically, so over the x-axis. And then the 2 means we're going to stretch by a factor of 2. So the -2 out here is a vertical flip and a vertical stretch by a factor of 2. And then the +1 at the end, what does that do? Let me
You're
start
going
with-
up.
Good, that's a shift up by 1 unit. So the transformations we need to apply in order are, first, shift 2 to the left. Then reflect vertically. That means over the x-axis. Then stretch vertically by a factor of 2. Then finally shift up 1 unit. All right. So we'll do these one at a time. Let me get a fresh sheet here. I'm going to start with the graph of 1 over x, and we're going to apply those transformations until we get there. Oh, the other way, sorry. So let me show you this. We've got space here. The other way to do this, instead of doing the long division, my calc professor called this the poor man's long division. He says x over x plus 2 is the same as x plus 2 minus 2 over x plus 2. All right, so I'm adding and subtracting 2 upstairs. I'm adding 0. That's kosher. That doesn't change anything. But then I can split this up as x plus 2 over x plus 2 minus 2 over x plus 2. And x plus 2 over x plus 2, those cancel. This is 1 minus 2 over x plus 2, which is what we got by doing the long division. So either way is fine. This poor man's long division works great as long as it's in this form, right? So like a linear thing divided by a linear thing, specifically if the lead coefficients are the same, like 1x upstairs and 1x downstairs, then this is quick and easy. But long division will always work. So this is the more general approach. All right. Let's draw the graph. I'm going to start with the graph y equals 1 over x. Which we all know and love. Does anybody know the name of this shape? The shape of the 1 over x graph? Just fun trivia. No? It's called a hyperbola, kind of like parabola, only hyperbola. When you hear people talk about being hyperbolic, that's a same root word, same root Greek word. Okay, so the first thing I need to do is shift this thing to the left by 2 units. So I'll come over here, 1, 2. This vertical asymptote is now going to be over here. So my new VA is the line x equals -2. My horizontal asymptote is still y equals 0. And if all I'm doing is that shift in this step, then the graph will look like this. The point 1, 1, if I move that 1, 2 to the left, becomes -1, 1. And the point -1, 1, if I move that 1, 2 to the left, that becomes -3, 1. And if I want to track the algebra, this would be the function y equals 1 over x plus 2. My next step is to reflect vertically. So I'll still have my VA over here at x equals -2. Still have my HA here, y equals 0.
Could you move the paper up a little bit for us, please?
Oh, yes, yes.
You say.
All right, so I'm just taking this graph and flipping it over vertically. That means that this branch up here is now going to be down here. And this branch, which was previously down here, is now going to be up here. So my point -1 comma +1 is going to go to -1, -1. And my point -3 comma -1 is going to go to -3 +1. And this would be the graph y equals -1 over x plus 2. So that's the vertical reflection. My next step is to scale everything vertically by a factor of 2, stretch vertically by a factor of 2. In order to keep things from getting too cluttered, I'll just do that down here. So let me label these two. This is the shift left 2 units. This is the reflect vertically. And this will be the scale vertically by 2. So what's going to happen there? We're just going to pick this whole graph up and like stretch it out. So in other words, I'm going to take all the y values on this graph and multiply them by 2. Again, at this step, my asymptotes don't change. But the shape changes just a little bit. This point is going to get stretched up. All the points are going to get stretched up, and I'll do my best to illustrate that, but it's a little tough. Something like this. And something like this. So if I take this point and stretch it up by a factor of 2, that's going to go to 3 comma 2. I'm sorry, -3 comma 2. And this point, -1, -1, is going to go to -1, -2. And now we're almost there. This would be the graph y equals -2 times 1 over x plus 2. The last thing I have to do here is shift vertically up by 1. And that will get me to my +1. Now shift up 1 unit. One of my asymptotes will change this time. Which one changes?
The horizontal asymptote?
Very good. The horizontal asymptote is going to move up by 1 unit. Okay. So I'll mark off here -1, -2, +1 here. So again, drawing in the asymptotes first, my HA moves up 1 to become the line y equals 1. My VA is still x equals -2. And then I just take the whole graph and I move it up 1 unit. So this point, -1, -2, is going to now be at -1, -1. And the rest of the picture is going to look something like, yeah, it's going to come up something like this. And then this branch over here has just been moved up by 1. So he's going to have the same sort of shape. Just he's going to be up here now. This point we said is now -1, -1. And the point -3, 2 is going to -3, 3. Again, getting bumped up 1. So this would be my final graph. This would be the graph y equals, I'll just write r of x. That was my original function. Not too bad. Not too bad, yeah? Most rational functions are not transformations of 1 over x, though. A linear function over a linear function can always be graphed this way. But you notice this is a little time consuming, right? Especially for the second guy. The first guy was very quick. But the second guy, we had to do some division, and we had a meaningful amount of other work to do. It would be nice if we had a general process that lets us graph any rational function, regardless of whether it's, ax plus b over cx plus d or something more complicated. And also that didn't require this sequence of graphs drawing so much stuff. It would be nice if we could get there just drawing one graph by finding certain information. So the things that we need to be able to find definitely include those asymptotes. So let's look at those asymptote rules. Finding asymptotes. This is going to be important all through Calc 1, through most of Calc 2, differential equations, so definitely hold on to this. Vertical asymptotes are easy. These come from factors of the bottom.
Can I ask a question about the last graph really quick?
Oh, sure, yeah.
What is the difference between shifting up 1 unit and stretching vertically? They seem very similar.
They do. So certain points can move the same way, but when you
move
shift
the
up 1
asymptote
unit,
up.
right? So
Yeah.
this portion of the graph, kind of, yeah, that's the big thing, right? The asymptote moves.
Yeah, I missed
So when
that
you
part. Thank you.
stretch, certain points will be fixed the same way they would be if you were to shift. But when you look at the whole picture, stretching is a little different than shifting, and the asymptote is the key. All right. So how do we find asymptotes? Vertical asymptotes come from factors of the bottom. And to find these, you need to solve the bottom is equal to 0. Horizontal asymptotes are more complicated. These come from a rule that needs to be split up into 3 different cases. It's based on the degree of the top and the degree of the bottom. So if the degree of the top is greater than the degree of the bottom, then there's not going to be any horizontal asymptote. If the degree of the top is strictly less than the degree of the bottom, then the HA is the line y equals 0. And that's like the last couple examples we saw. If the degree of the top is equal to the degree of the bottom, like the very last example we saw, then the horizontal asymptote is going to be something else. And that something else is found by taking the ratio of lead coefficients. So it'll be the line y equals, and I'm going to write it out like that, ratio of lead coefficients. Meaning you take the lead coefficient of the top and divide it by the lead coefficient of the bottom. That will be your horizontal asymptote. Y equals that number. Okay, so let's just do something really quick where we find some asymptotes. The function r of x equals 2x squared minus 4x plus 5 over x squared minus 2x plus 1. Here's the deal. The first step, in addition to this like finding asymptotes business, I'm going to give you like a 5-step process for graphing rational functions. The very first thing we always do is factor the top and the bottom, if possible, right? Try to factor the top and the bottom. I know that if I'm looking for the vertical asymptote or asymptotes, those are going to come from factors of the bottom, right? Factors of the bottom. Solving the bottom equal to 0 is the same thing as saying factor the bottom, right? Because where is the bottom equal to 0? Well, it depends on the factors of the bottom. So how does x squared minus 2x plus 1 factor?
X minus 1, like parentheses x minus 1.
Very good. Another way of saying that is x minus 1 all squared. Now the top here doesn't factor. We don't need it. But I should put a little asterisk on the thing for vertical asymptotes, which I'll explain in just a second after we've gone through this. So my VA comes from where the bottom is equal to 0. And the bottom is equal to 0 if and only if x is equal to 1. So that's my vertical asymptote. There's only one of them, and it's x equals 1. What is my horizontal asymptote?
2.
Very good. The degree of the top and the degree of the bottom are the same. These are both quadratics. So we take the ratio of lead coefficients. The lead coefficient of the top, so the degree of the top is equal to the degree of the bottom. So my HA is y equals the lead coefficient of the top, which is 2, divided by the lead coefficient of the bottom, which is 1, and 2 over 1 is 2. All right, that's it. We found the asymptotes. I want you to leave a good chunk of space. Oh, no, actually, we'll just come back and redo it. So what I'm going to do next is share with you that full process for finding the graph, for sketching the graph. And then we're going to come back and we're actually going to do that. We're going to sketch the graph of this function and then a few others afterwards. But we'll treat them as separate examples. So to sketch the graph of a rational function, we want to do the following things. First, factor top and bottom. Then find vertical asymptotes. Find horizontal asymptotes. Then find intercepts, x-intercepts and y-intercepts. Your x-intercepts, these come from factors of the top. I.e., you have to solve the top is equal to 0. That doesn't require going off and setting up a separate equation because you will have already factored the top and the bottom. And the reason for this, why are x-intercepts going to come from factors of the top or places where the top is 0? Well, you've got here a big fraction, right? The only way to have a big fraction all equals 0, remember x-intercepts are where the whole function is equal to 0, is if the top is 0. Like 0 over 5 is 0. 0 over 10 is 0. 0 over -2 is 0. So if the top is 0, then the whole function will be 0. And that's what it means to say you've got an x-intercept. Y-intercepts, there's nothing special about rational functions. Y-intercepts for any function you find by plugging in x equals 0. And then your last step here is going to be to determine the local behavior near your x-intercepts, which follow the same rules as polynomials. This is based on multiplicity. And near your VAs, near your vertical asymptotes. And these are also based on multiplicity. Notice that there's two features here that come from factors. The x-intercepts come from factors of the top, and the multiplicity of those factors will tell me the local behavior near those x-intercepts. The other feature that comes from factors are the vertical asymptotes, right? Vertical asymptotes come from factors of the bottom. So they also have an associated multiplicity. Finally, you may maybe plot a few points. If necessary. Then draw the graph. All right. So this is your procedure. Let me share with you the story behind that asterisk at the top. Right. So what's the asterisk here? The vertical asymptotes come by solving the bottom equal to 0. They come from factors of the bottom. But you have to be careful about factors that may cancel. So if a factor from the bottom cancels with a factor from the top, this will produce a hole, not a vertical asymptote. That's the little asterisk there. But for the most part, this is accurate, right? Saying that vertical asymptotes come from factors of the bottom. But if that factor happens to cancel with a factor of the top, well, then that factor really doesn't belong down there, and there really isn't a vertical asymptote coming from it. So what I'd like to do next is sketch the graph of this function right here. We've already found the vertical asymptote and the horizontal asymptote, so we can go ahead and get to it using this procedure. Make sure you have all of this stuff nice and clear in your notes, the procedure for graphing rational functions and the procedure for finding asymptotes. because that's the bulk of the material that we need for this section. The one thing in this 5-step procedure that hasn't been explained is how you get the local behavior near the vertical asymptote. So let me give you that story also. The function will change sign over a VA with odd multiplicity. And will not change sign at a VA with even multiplicity. So what I mean by that is if you have a vertical asymptote coming from an odd multiplicity factor, then if one arrow goes up, the other arrow goes down, like 1/x, right? That vertical asymptote at 0, the arrow goes down on the left and up on the right. That's because the x downstairs is an odd multiplicity factor. If you think about the graph of 1/x squared, both arrows go up on that. And that's because the x squared downstairs is an even multiplicity factor. Okay, so let's try to sketch a quick graph of this guy from above. The top here, so we already factored the bottom. The top here doesn't factor, so I just leave it alone. Now, I might think that the top doesn't factor because the roots are irrational, or maybe it's because the roots are non-real complex numbers. So we should check. B squared minus 4AC for this guy is -4 squared, which is 16, minus 4 times 2 times 5, which is 40. So this is -24. So this is irreducible. No real roots, no real zeros. So that top, there's no real number that makes that top 0. So that means that there's not going to be any x-intercepts. So my first step, factor top and bottom, is done. Next up, I want to.
Can we use imaginary numbers?
Yeah, but your graphs don't have imaginary numbers on them, right? My x-axis and y-axis are both real numbers. So yes, there are imaginary numbers or complex numbers you can plug in to make this thing 0, but that won't show up anywhere on the graph. I think we're asking about the note here. So a function will change sign over a vertical asymptote with odd multiplicity and will not change sign at a vertical asymptote with even multiplicity. Oh, up here. So if a factor from the bottom cancels with a factor from the top, this will produce a hole, not a vertical asymptote. Yeah, so if a factor from the bottom cancels with a factor from the top, this will produce a hole, not a vertical asymptote. All right, but we don't have any of that weirdness to worry about here. So next I need to find my intercepts. The x-intercepts here, we already said those would come from the top equaling 0, but this, there are no real solutions. So there's no x-intercept. The y-intercept comes from plugging in 0 for x. And r of 0, what you get when you plug 0 in here, it's easier to see from this form. That's going to be 2 times 0 minus 4, sorry, 2 times 0 squared minus 4 times 0 plus 5, which is 5, over 0 squared minus 2 times 0 plus 1. This is 5 over 1, which is 5. So my y-intercept is 5. Let's find the vertical asymptote. We already found that. We know that's the line x equals 1, and the multiplicity here is 2. The horizontal asymptote, oh, we said that was a separate number, didn't we? Yeah, so therefore, the horizontal asymptote is going to be the ratio of lead coefficients. We also already found that. And now we can start plotting stuff. So here's my horizontal asymptote. It's the line y equals 2. My vertical asymptote is the line x equals 1. Intercepts, I didn't have any x-intercepts, but my y-intercept is 5. So this is 2, this would be 5. There's my y-intercept. And now the trick is, just with this very sparse bit of information, to try and figure out what's going on near these asymptotes. Do I have arrows up here? Do I have an arrow up here or down here? Do I have an arrow up here or down here? Do I have arrows down here or down here? So I want to fill in the arrows around my vertical asymptotes and around my horizontal asymptotes. The key to getting started is this y-intercept. I know that my function is positive at x equals 0, right? R of 0 is positive 5. So as I'm sneaking up on this asymptote, the question is, does the arrow go up or does the arrow go down? Who can answer me that question? Is it possible for the arrow to point down? Is it possible for me to have an arrow here going down, for me to approach this asymptote going to negative infinity like that?
No, because it would cross the horizontal asymptote.
Well, crossing the horizontal asymptote is okay. That's not a problem, but you're very, very close. What can I not cross?
X-axis, because we don't have any x-intercept.
Beautiful. There are no x-intercepts. And in order for me to get from here to down here, I would have to cross the x-axis somewhere in here. That would mean there's an x-intercept in there, but there isn't. We know that. We know there are no x-intercepts. So that means this arrow must go up. Next, I'd like to fill in the arrow on the other side here. Is it up or is it down?
Up also because there's no x-intercept.
Fair enough. Yeah, if this arrow was pointing down, then to get over here to my horizontal asymptote, I would have had to have crossed the x-axis again. Another way we could get there, the multiplicity. So this vertical asymptote comes from an even multiplicity factor. And remember what we said, if you go over a VA from an even multiplicity factor, you will not change sign. So if you're positive on the left of it, you'll be positive on the right of it. If this was a multiplicity 1 or multiplicity 3 vertical asymptote, then I would be down here on this side. But because it's an even multiplicity factor giving me this vertical asymptote, I know that the arrows have to point the same way on either side, just like 1 over x squared. Okay, now, if I'm up here and I'm going to cross through here and I have to approach this horizontal asymptote, then I'm approaching it from above. And similarly, if I'm up here and I'm going to approach this horizontal asymptote, I'm approaching it from above. So my graph is like this. Right, and it goes up and up and up here forever. Forever and ever, amen, always sneaking up on this guy. It's not true that you cannot cross an HA. You can cross an HA. And there might be some concern that maybe I come down here, don't hit the x-axis, but turn around and come back up like this. It's possible that I come down here and then turn around and come back up like this. If you were uncertain about that, the thing to do would be to plug in some x values over here, right? Specifically plug in some x values far away over here. And you'll see that the function is greater than 2 over here and greater than 2 over here. So if you're uncertain about whether you should be approaching these HAs from above or below, you could plug in like -10 and +10 to your function. And that's where we might make a little table just to make sure that we're doing everything right. Now I'll let you do this because I don't want to burn the time on it, but you'll see that it is correct. If I plug in like -10, then this is 2 times 100 minus 4 times 10 plus 5. So that's 200 minus 40 is 160. Plus 5 is 165. Divided by 100 minus 20 is 80 plus 1, which is a little bit bigger than 2, right? It's actually pretty close to 3. And if you plug in +10, you get the, oh, actually, that's the +10 version, isn't it? Yeah, -10. That would be 2 times 100 is 200 plus 40. So that's 240 plus 5 is 245 divided by 100 plus 20 is 120, 121. And both of these are bigger than 2, right? That numerator is more than twice that denominator. That numerator is more than twice that denominator. So both of those are above the line y equals 2, which means we have to be approaching this from above. So this is the point. -10, comma, 245 over 121. That's the point. +10, comma, 165 over 81. You can use your calculator to get a decimal if you're uncertain whether that's bigger or smaller than 2. All right, and this is a really nice graph. We can compare with what Desmos says. I'm pretty confident it's good, but let's do it. There she is, looking mighty good. And here's that x value we plugged in just to check. See, it's a little bit bigger than 2. Little bit bigger than 2. And that means we've got to be approaching that horizontal asymptote y equals 2 from above. VA, x equals 1 is right here. Not too bad, right? Okay. Let's try one more. I think we've got one more, as room for one more here, as long as we work at a reasonable pace. let's sketch r of x equals 2x squared plus 7x minus 4 divided by x squared plus x minus 2. My first step is to factor the top and the bottom. The bottom factors as x minus 1 times x plus 2. These are both just quadratics. Upstairs, you would need that full AC method thing. 2 times -4 is -8. Middle term is positive 7. So you got to find two numbers that multiply to -8 and add to positive 7. That would be 8 and -1. And then you'd write this as 2x squared plus 8x minus 1x minus 4. And when you get everything done, you're going to have 2x minus 1 times x plus 4. So my intercepts x-intercept, there's going to be two of them. These come from the factors of the top. So those are x equals 1/2 and x equals -4, and both are multiplicity 1.
Would it be a mistake if we're just gonna write x minus 1/2 on top? I mean, if you're gonna solve it, or we should
If
write.
you're going to write x minus 1/2, that would be, you have to factor out the 2. So that would be 2 times x minus 1/2 times x plus 4 over x minus 1 times x plus 2. So that would be okay. All right. So we've got our x-intercepts. What about our y-intercept? How do I find the y-intercept?
1 and -2, because it's on the bottom.
Careful. Factors of the bottom give us something else, and you can only ever have one y-intercept. So go ahead and look at the steps there. What was the rule for finding y-intercepts?
You set x to 0.
Yeah, we plug in x equals 0. So what is r of 0 here? Well, it's 0, 0, -4 divided by 0, 0, -2, which is positive 2. My vertical asymptotes, where do these come from?
From the x squared plus x minus 2 equal to 0.
Yeah, they come from the bottom, right? And we've already factored the bottom. So that's x squared plus x minus 2 is x minus 1 times x plus 2. So where is this equal to 0?
1 and -2.
Very good. So those are my two vertical asymptotes. What about my horizontal asymptote?
It's gonna be 2.
Great, very good, right? Because again, the top and bottom are both quadratic. They have the same degree. So I'll take the ratio of lead coefficients, which is 2/1, which is 2. All right. Now we're ready to get working. Okay, so I've got a bunch of stuff I need to graph here. We're going to go as far left as -4. So I'm mark -1, -2, -3, -4. I have a vertical asymptote here. Other VA is, oh, wait. Nope, oh, God damn it. Sorry, not a VA at -4. Stuff. We have something out there at -4. It's just not a vertical asymptote. -1, -2, -3, -4. It's an x-intercept, right? We have an x-intercept out here at -4. And we also have an x-intercept at +1/2. So if here's 1, 2, 3, and so on, here's the point 1/2, 0. What else do I have going on? Y-intercept is +2. So here's 1, 2. Now let's get the asymptotes in. So the vertical asymptotes are -2, and +1. I'll label those. I have a horizontal asymptote, and here's an example of a graph touching its horizontal asymptote, right? That y-intercept is right there on the horizontal asymptote, and that's okay. There are actually functions that touch their horizontal asymptote infinitely many times. This guy just hits it once, I think. All right, that's all of the points that I have so far, and that's all the points I'm going to need. Now what we're going to do is use what we know about the asymptotes and their multiplicities. These were both also multiplicity 1. To try and sort out the arrows associated with each asymptote. So I'm arriving at this horizontal asymptote here, coming up from this x-intercept. So I'm going to approach this HA from beneath, like that. Which means I'm going to do something like this. We're going to cross at this x-intercept because it's an odd multiplicity root. And that means I'm coming down as I approach this vertical asymptote. So this arrow goes down.
Professor, why can you cross the horizontal asymptote but not the vertical asymptote?
It's a good question. So a vertical asymptote comes from the bottom being 0. Imagine you did have a point right here on this vertical asymptote. How would you get that y value? You would get it by plugging -2 into this function. But if you plug -2 in here, the whole thing becomes undefined. So for rational functions, vertical asymptotes are always places where the function is undefined, which means it's impossible to have a point exactly on the vertical asymptote. But there is no such thing with horizontal asymptotes. Horizontal asymptotes just come from the ratio of lead coefficients. So there's no harm here, right? These aren't associated with any domain issues the way vertical asymptotes are. So it's a good question. It turns out if you allow me to fuck around with things a little bit, you can touch a vertical asymptote, just not for a rational function. If you let me piecewise define a function, then I can make it touch its vertical asymptote. But it feels unnatural, and a rational function will never do that, because the VAs come from places where the bottom is 0, which means the function is automatically undefined there. All right, I know we're a little bit over time, so let's get this done. This arrow goes down because we're coming through this x-intercept like this, right? So in order to go, if I was going to go up here, I would have to have another x-intercept, and I don't. If this arrow goes down, what does the arrow on the other side do? Does it go up or down? You can think about this y-intercept. This y-intercept is positive, right? And I don't have any x-intercepts in here. So in order to connect a down arrow here to this y-intercept here, I would have to have had an x-intercept there. Or, because we know that this guy comes from a multiplicity 1 factor, the function must change sign as we hop over that. So since we're negative over here, we must be positive over here. Which tells me then, okay, I'm coming in from above here. I have to go through this y-intercept. Then I need to go through this x-intercept. Since I'm coming in from above, I'm crossing to below because that's an odd multiplicity intercept, which means I'm arriving at this asymptote going down also. And then again, because this asymptote comes from an odd multiplicity factor, if the arrow goes down on one side, it has to go up on the other. And that means that I have to be arriving at this horizontal asymptote from above. So here is my kind of framework. Just like the end behavior and the local behavior near the roots was your framework for drawing a polynomial graph, all of these little arrows and crosses and touches, these tell me how to draw the graph of the rational function. Now you just connect the pieces. So this is going to be something like this, and going out forever like that. This guy has to go through here, down here. So something like that. And this has to connect to this. So that's going to be something like this. All right, so there's your graph. And it is a pretty complicated graph. Now, I'm not going to pretend like it's not. This requires some work, but it's far from impossible. We can definitely do it. Once you have the asymptotes, the x-intercepts, and one point where the function isn't 0, as long as you know the multiplicity of each asymptote and each x-intercept, you can fill in the rest. So knowing that this was positive tells me that this arrow goes up, tells me that this arrow goes down, tells me that I cross from below to above, tells me I approach this from beneath. And since this is positive and this is odd multiplicity, I know I have to cross here, which means I approach this from below. Since the VA is odd multiplicity, I have to come back from the other side, which tells me I approach this from above. And if we were uncertain, then we could always plot a few points, right? If you're not sure whether this should come up from below, you could plug in like x equals -10 and see if that's smaller than 2 or bigger than 2. You could, if you're not sure whether this should be above or below, plug in like x equals +10 and see if that's bigger than 2 or smaller than 2. But you shouldn't need to make a big table for these. And if you find yourself making a big table on these problems, something has gone a little wrong. You want to make sure you go back and understand the rules associated with multiplicities. If you need to rewatch this lecture, please do that. That's not a bad thing. But take the time to practice this. And as you work these homework problems, please, for the love of God, draw the graphs by hand, then match them to the stuff in WebAssign. Don't just click around, because you won't learn that way, I promise you, and then you'll be in trouble on the test. So take the time to learn how to do this right, the way we did it here in class today, and you will nail this next test. If you eschew all of this stuff, if you don't do it and you just try to get there by clicking around or plotting points, then you're going to run into trouble on the test. And I don't want that for you. If any of it feels hard, you feel lost, struggling, frustrated, whatever, just bring problems by the office hours. If you can't do that, send pictures of your work to me on Desmos or on Discord or through Canvas. I'll be happy to help. But please work hard on this stuff. And that's it. All right. So next time we're going to look more at rational functions. I'll show you some stuff where holes appear, right? Like factors at the top and bottom cancel, and a few other kind of weird things that can happen. In parting, let's take a look at what Desmos says this thing looks like, and we'll see how good we did. So this was 2x squared plus 7x minus 4 divided by x squared plus x minus 2. There she is. Not too shabby, right? Look at that. Here, let's center it so it looks the same, right? Not bad at all. If we slap in those asymptotes, looks exactly like ours. And I don't know about you, I am real happy with this. This and this look very much the same to me. So I would call that victory. You're going to need to practice this. It's not something that's going to happen automatically. It's not going to happen just from watching other people do examples. You're going to need to practice it. You'll make mistakes. That's okay. Just make sure you take the time to work through them. And if you're ever stuck on anything, you're not getting anywhere, you feel like it's getting to be frustrating, please ask for help, because I'm here to help and I'm happy to do it. Rational functions are beautiful, man. There's so much we can do with these. So let's take the time here and it'll pay off later in this course and in Calc 1, Calc 2, Calc 3. That's it from me for today, guys. I hope you have a lovely rest of your day, and I will see you on Tuesday of next week.